Somewhere above our cities, above the thin veil of clouds and weather, above the last blue hints of air, the night keeps doing the same simple thing it has always done. It holds still, and it shines. If we let our eyes adjust long enough, the sky becomes more than a backdrop. It becomes a map. Stars are not scattered at random. They gather into bands and clusters. A faint river of light crosses the darkness, and we learn to call it the Milky Way. And when we remember that every bright point is a sun, and every faint blur is a galaxy, the calm night starts to feel immense. But the universe is not only a picture, it is motion. Galaxies rotate slowly, with a kind of patient insistence. Some complete a turn in a few 100 million years. Others take longer. Clusters of galaxies, enormous congregations of matter, orbit their shared centers of gravity. Entire clusters collide and pass through each other on timescales that make human history feel brief. Light from distant galaxies bends as it travels through space, and the oldest light we can detect, the cosmic microwave background, carries a fossil imprint of waves that moved through an early cosmic plasma and then froze into place. In all of these motions, we keep finding the same quiet discrepancy. The gravity we can measure seems too strong for the matter we can count. That is the center of tonight's story. Dark matter is the name we give to whatever is adding gravity without adding light. It does not glow. It does not scatter and absorb in ways that our telescopes can easily track. It does not announce itself with bright lines in a spectrum or with radio pulses. As far as our best instruments can tell, dark matter interacts very weakly with ordinary matter, except through gravity. But we should be gentle about the language. Dark matter is a label, not a final answer. It is a placeholder for a missing ingredient in our description of the universe. It tells us that something is there because gravity responds to it, but it does not tell us what the thing is made of. This matters because if we are not careful, a placeholder can start to feel like a solved problem, when the truth is that we are still searching for the underlying substance. So tonight we will do two things at once. We will treat the evidence seriously because it is broad and persistent, and it connects across many independent methods. And we will also treat the unknowns seriously because dark matter is still one of the biggest unanswered questions in physics. We will ask, what do we actually know, in a way that is backed by measurements? What do we still not know? And what could plausibly change next? As we move, we will separate three categories of statements. First, observations that are broadly accepted as robust. These are repeated measurements that remain stable as instruments improve. Second, interpretations that are strongly supported, but still involve modeling choices. These are places where dark matter fits well, but where the details can shift as we learn more about how galaxies really behave. Third, ideas that are still speculative. These can be elegant and important, but they are not verified. When we touch them, we will label them as speculation, so the difference stays clear. To begin, we need one simple tool: the ability to weigh the universe. We cannot put a galaxy cluster on a scale, but we can do something almost as good. We can watch how things move inside it. We can measure how hot its gas is. We can look at how it bends light. And from each of these, we can infer the gravitational pull, and therefore the mass. This is the core logic behind the dark matter story. When gravity is strong, it leaves signatures. When mass is present, it shapes motion and light. The first hints came when astronomers began to do these measurements carefully and noticed that the inferred mass kept coming out much larger than the luminous mass. At first, this could be dismissed as uncertainty. Maybe our distances were wrong. Maybe we misunderstood how bright stars are compared to their mass. Maybe gas was hiding in forms we had not accounted for. Maybe clusters were not in equilibrium, making a mass estimate unreliable. Those are all reasonable concerns. Science advances by pushing on its weak points. The reason dark matter endured is that the discrepancy did not vanish as the data improved. It appeared in different systems, measured by different methods, and the same basic message kept repeating. There is more gravitating mass than we can see. It is also important to say what dark matter is not. Dark matter is not simply dark stuff in the everyday sense. Ordinary matter can be dark too. Cold gas, dust clouds, objects that do not shine. But ordinary matter interacts electromagnetically. It absorbs and emits radiation at specific wavelengths. It can be tracked with radio telescopes, infrared surveys, ultraviolet spectra, X-ray satellites. Large amounts of ordinary baryonic matter cannot hide perfectly because they leave fingerprints in the way they heat, cool, scatter light, and produce lines in spectra. Dark matter is also not the same as dark energy. Dark energy is tied to the acceleration of cosmic expansion and behaves differently in the equations of cosmology. Dark matter behaves, to a first approximation, as matter. It clumps, it forms halos, it pulls things together. So when we say dark, we mean dark to our telescopes, not necessarily dark in a poetic sense. We mean that whatever it is not interacting with light in the ordinary ways. And that sets up the mystery. Because if dark matter does not interact with light, we cannot photograph it directly. We cannot point a telescope at it and see it glowing. But gravity can still show us where it is, and how much there is. So we begin with the first place where the mismatch became hard to ignore. Clusters of galaxies. A galaxy cluster is not a single object. It is a collection, a gravitational family. Hundreds or thousands of galaxies orbit a shared center of mass. Between them lies hot, diffuse plasma that can reach tens of millions of degrees and glow in X-rays. And around all of it, the cluster's gravity shapes the motions of everything inside. If we want to estimate the mass of a cluster, one of the oldest approaches is to measure how fast its member galaxies are moving. This is the basic logic. In a bound system, motion and gravity are linked. If the galaxies are moving quickly, gravity must be strong to keep the cluster together. If gravity is weak, the galaxies would drift apart over time. In the early 1930s, Fritz Zwicky studied the Coma cluster and applied this reasoning. He compared the mass implied by galaxy motions to the mass implied by the cluster's visible light. The results suggested that Coma required far more mass than the luminous galaxies could provide. Even today, when we revisit these early calculations with improved data, the missing mass pattern remains, though our numbers and uncertainties are far better. One reason clusters are persuasive is that there are multiple ways to weigh them, not just one. We can look at the motion of galaxies inside the cluster. That gives a dynamical mass estimate. We can measure the temperature and distribution of the hot intracluster gas. Gas in hydrostatic equilibrium inside a gravitational potential well has a temperature profile related to the depth of that well. From X-ray observations, we can infer how massive the cluster must be to confine such hot gas. This method has caveats. Clusters can be disturbed. Collisions can break equilibrium, but it adds an independent line of evidence. We can also use the Sunyaev-Zeldovich effect, where hot electrons in the cluster scatter photons of the cosmic microwave background and slightly change the CMB spectrum in the cluster direction. Combined with X-ray data, this can constrain the gas properties and, indirectly, the cluster's mass distribution. And we can use gravitational lensing, which we will explore soon, to map mass directly through its effect on light. When multiple methods point to the same conclusion, that clusters contain much more mass than luminous matter, the argument becomes harder to dismiss as a single systematic error. Now we come closer to home, into individual galaxies. A spiral galaxy is a disk of stars and gas. The disk rotates. We can measure that rotation by observing Doppler shifts, how the wavelength of light or radio emission changes when something moves toward or away from us. For stars, we can measure this through optical spectra. For gas, especially neutral hydrogen, we can use radio observations of the 21-centimeter line. Neutral hydrogen extends far beyond the bright stellar disk in many galaxies, reaching into faint outer regions where starlight becomes scarce. Rotation curves plot orbital speed against distance from the galaxy center. If most of the mass were where the light is, if the mass distribution followed the bright disk, then, as we move outward beyond the main luminous region, the orbital speeds should decline. Gravity would weaken, and outer orbits would slow. But that is not what we see. In many galaxies, the rotation speed remains roughly constant far beyond the visible disk. The outer hydrogen gas still orbits quickly, as if it is held by an extended gravitational halo. There is a quiet, practical beauty to this evidence. It is measured with different tools across many galaxies, and the pattern repeats. Vera Rubin and collaborators played a major role in establishing the prevalence of these flat rotation curves. Over time, the result became part of the standard picture. Galaxies are embedded in extended halos of unseen mass. We can also understand this with a simple scaling argument. If speed remains constant as radius increases, the enclosed mass must continue to grow with radius. That implies mass extends outward well beyond the region where most stars reside. Of course, galaxies are not perfect spheres and not perfect disks. They have bars and spiral arms, and gas does not always move in purely circular orbits. That can add complexity to rotation curve interpretation. But the overall need for additional gravitational mass remains robust across many systems. There is another striking aspect. The effect tends to be stronger, relative to starlight, in smaller and fainter systems. Low surface brightness galaxies can be spread out and faint, yet still rotate with speeds that imply large halos. Many dwarf galaxies show dynamics suggesting that their visible stars are a small tracer in a much larger gravitational well. Dwarf spheroidal galaxies, which often orbit larger galaxies as satellites, are especially interesting. They contain little gas and few stars, but their stars move with velocity dispersions that imply significant mass. Their mass-to-light ratios can be very high. These systems are often considered dark matter-dominated, though the detailed modeling can be subtle and depends on assumptions about stellar orbits and anisotropies. Still, the message remains. In many galaxies, the gravity we infer is larger than the luminous matter can account for. At this stage of the story, a skeptic could still ask whether the missing mass is ordinary matter we have not detected. Could it be a population of faint stars, brown dwarfs, cold clouds, compact objects? Could it be gas in difficult-to-detect phases? Those possibilities were explored, and they remain part of the historical development. But as the evidence expanded, especially with cosmological constraints, ordinary baryonic matter became harder to hide in the quantities required. We will return to compact object possibilities later, because some remain under discussion in certain mass ranges, but the large-scale cosmological evidence points strongly to a non-baryonic component. For now, the first clues were clear enough to motivate a new idea: matter that adds gravity without adding light. But to strengthen an idea, we want independent methods. And one of the cleanest independent methods is the bending of light itself. Gravity shapes the paths of light. This is one of the most quietly profound results of general relativity. Light does not travel through space as though space were an empty stage. Space has geometry, and mass changes that geometry. So when light from a distant galaxy passes near a massive object, its path bends. The foreground mass acts as a gravitational lens. Sometimes the effect is dramatic. A background galaxy can be stretched into arcs. Sometimes a near-perfect alignment creates an Einstein ring, a luminous circle around the foreground object. Sometimes multiple images of the same background galaxy appear, each one following a different bent path through curved space-time. Other times the effect is subtle. The shapes of many background galaxies are slightly stretched and sheared. By studying the coherent pattern of that shear, we can reconstruct a map of the foreground mass distribution. This is weak lensing. Lensing is powerful for dark matter because it measures gravity directly, without caring whether the mass is luminous. A galaxy cluster can be weighed by lensing even if much of its mass is not emitting light. When lensing is applied to clusters, it confirms what dynamics and X-ray measurements suggest. Clusters contain much more mass than their luminous content. But lensing becomes especially compelling in cluster collisions, because collisions separate different components of matter in space. Here is the key point. Galaxies, being mostly empty space, pass through collisions with relatively little direct interaction. They are slowed by gravity, but not by strong drag forces. Hot intracluster gas, however, behaves like a fluid. It interacts electromagnetically. When two clusters collide, their gas clouds shock, heat up, and slow down. The gas often ends up displaced from the galaxies after the collision, glowing in X-rays in a region where it has been compressed and heated. This sets up a natural experiment. Where is the mass after the collision? If the mass is mostly in the gas, if ordinary baryonic matter dominates, then the gravitational potential should be centered on the gas. If the mass is mostly in an unseen, collisionless component, then the gravitational potential should stay aligned with the galaxies. The bullet cluster is a famous example of this experiment. X-ray observations show hot gas concentrated in a region offset from the galaxies. Lensing reconstructions map the gravitational potential and show mass peaks offset from the gas, aligned more with the galaxies. The simplest interpretation is that each cluster had a halo of dark matter. During collision, the halos passed through each other with the galaxies, while the gas was slowed. Lensing then traced the halos and galaxies, not the gas. This is not the only merging cluster studied this way. Other systems have provided similar evidence, though each with its own complexities, and the overall message remains. The dominant gravitating mass behaves as collisionless in these collisions, while baryonic gas behaves as collisional. It is worth slowing down here and being precise about what we learn. Lensing does not show us a glowing dark matter cloud. It shows us where gravity is strongest. The inference that this gravity comes from dark matter is strongly supported because the gravity peaks are separated from the baryonic gas, which contains much of the ordinary matter in clusters. This evidence is also useful for constraining dark matter self-interactions. If dark matter particles scattered off each other frequently, the halos might behave more like a fluid and experience drag in collisions, altering the separation pattern. The persistence of separation suggests that on cluster scales, dark matter is at most weakly self-interacting. The exact numerical constraints depend on modeling and on how we interpret the collision geometry and timing, so we treat them with care. But the qualitative conclusion that dark matter is largely collisionless in these environments is robust. There is also a quieter form of lensing evidence that supports the halo picture on galaxy scales. Galaxy-galaxy lensing uses the statistical distortion of background galaxies to infer the average mass distribution around foreground galaxies. When we do this across many systems, we find that galaxies are surrounded by extended mass distributions consistent with halos larger than the luminous disks. So lensing reinforces the rotation curve picture from a different direction. Rotation curves use motion within galaxies. Lensing uses the bending of light behind galaxies. Now our network of evidence is wide. We have cluster dynamics and gas temperatures. We have galaxy rotation curves. We have lensing mass maps. We have cluster collision separations. And still, there is one more pillar, perhaps the most powerful on the largest scales. The early universe itself, recorded in the oldest light, tells us how much matter existed and how it behaved. There was a time when the universe was too hot for atoms. Matter existed as a plasma of electrons and nuclei, and photons were trapped by constant scattering. In that era, the universe was opaque. As the universe expanded, it cooled. Eventually, electrons combined with nuclei to form neutral atoms. When that happened, photons were no longer scattered constantly. They streamed through space. Those photons are still traveling today. They have been stretched by cosmic expansion until they are microwaves. We detect them as the cosmic microwave background, the CMB. The CMB is a snapshot of the universe when it was about 380,000 years old. It is remarkably uniform, but not perfectly. It contains tiny temperature fluctuations that reflect small density variations and gravitational potentials in the early universe. These tiny variations are the seeds of structure. Gravity amplifies over densities. Matter falls into regions that are slightly denser than average. Over time, halos form. Gas cools, stars ignite, galaxies assemble, clusters grow, filaments stretch between them, voids expand where matter is scarce. So the CMB is both a relic and a blueprint. And because the physics of the early universe can be modeled with high precision, the CMB allows us to infer the composition of the universe, including the abundance of dark matter. The key idea involves acoustic oscillations. In the early plasma, photons and baryons were coupled. Gravity pulled matter inward, trying to deepen density wells. Radiation pressure pushed outward, resisting collapse. This created oscillations, sound waves, in the photon-baryon fluid. When the universe became neutral and photons decoupled, the pattern of these oscillations was frozen into the CMB. In the angular power spectrum of the CMB, these oscillations appear as peaks. The relative heights and positions of the peaks depend on baryon density, total matter density, and dark matter density. Baryons add inertia to the oscillating fluid. Dark matter does not couple to photons the same way, so it affects the gravitational wells and the overall balance differently. Precision missions such as Planck measured the CMB anisotropies with extraordinary accuracy. Within the standard cosmological framework, the results constrain the dark matter density parameter, often expressed as omega CH squared, to be around 0.12 with a small uncertainty. This is astonishing when we pause to reflect on it. It means that by measuring faint temperature fluctuations in microwaves across the sky, we infer the existence and abundance of a matter component that does not emit light and that dominates the matter budget. CMB constraints also align with Big Bang nucleosynthesis constraints on baryons. The light element abundances indicate a baryon density consistent with the CMB result, and that baryon density is not enough to account for all matter. So most matter must be non-baryonic. Now we move from the early universe to the later universe to structure formation. Dark matter matters because it can begin clumping early. While baryons were coupled to radiation, Baryonic matter could not collapse easily into small-scale structures. Radiation pressure resisted it. Dark matter, if it does not couple to photons, can begin to form gravitational wells earlier, providing places for baryons to fall into once the universe becomes transparent. In this picture, dark matter forms halos and filaments first, and baryons follow. This helps explain why structure can grow from tiny initial fluctuations to the large cosmic web we observe today. We see that web in galaxy surveys as filaments and clusters. We also see it in gravitational lensing maps on large scales, and in the distribution of gas traced by various observations. Numerical simulations that include cold, dark matter and start from CMB-consistent initial conditions reproduce many large-scale statistical properties of the cosmic web. This success is one reason cold dark matter is a central component of the standard cosmological model. But we keep the nuance close. Simulations involve assumptions, and baryonic physics can change small-scale details. On the largest scales, however, the cold dark matter model has been notably effective at reproducing observed patterns. This brings us to an important distinction. Dark matter refers to gravitational effects, but it also refers to a physical component of the universe's inventory. The CMB and large-scale structure provide strong evidence that a non-baryonic matter component existed early and shaped structure growth. Now, after walking through the evidence pillars, we can summarize what we know about dark matter's properties in constraint form. We have not yet held dark matter in our hands. We have not yet taken a spectrum of it. We have not yet watched it interact clearly and repeatedly in a laboratory detector. So what we know is a silhouette drawn from gravity and cosmology. Even so, that silhouette has edges and structure. 1. Dark matter is not mainly made of baryons. The baryon density is constrained by the early universe. Big Bang nucleosynthesis and the CMB together limit how much ordinary matter exists. That baryonic budget is too small to explain the total matter density required by cosmology and by large-scale structure. Therefore, the dominant matter component must be non-baryonic. 2. Dark matter dominates the matter budget. In the standard cosmological model, dark matter provides most of the matter that clumps under gravity. Ordinary matter is a smaller fraction. This is why we can say, in plain terms, that most matter in the universe is invisible to our telescopes. 3. Dark matter must be cold or effectively cold in the cosmological sense. Hot, relativistic dark matter would erase small-scale structure by free streaming. Observations of the cosmic web and of galaxies indicate that the dominant dark matter component must allow small structures to form. Cold dark matter fits this requirement. Warm dark matter remains possible in certain models, but it must be consistent with small-scale observations and the matter power spectrum. 4. Dark matter interacts weakly with electromagnetism. If dark matter carried ordinary electric charge, it would absorb and emit light and would be detectable in many ways. Its darkness means any coupling to light is extremely small or absent. Dark sectors with their own forces are possible, but coupling to ordinary photons is tightly constrained by observations. 5. Dark matter is distributed in halos and larger structures. On galaxy scales, rotation curves and lensing indicate extended halos. On cluster scales, dynamics, gas temperatures, and lensing indicate deep gravitational wells dominated by unseen mass. On cosmic scales, large-scale structure indicates that matter is arranged in a web consistent with a dominant dark matter component. 6. Dark matter behaves as collisionless on many scales we can test, though self-interactions are still an open question. Cluster collisions suggest that the dominant gravitating mass passes through collisions with little drag, unlike baryonic gas. This supports a collisionless description. Some models propose self-interacting dark matter with cross-sections small enough to evade cluster constraints, but large enough to affect small scales. This remains an active topic, and we will return to it later. 7. Dark matter is stable or effectively stable over billions of years. If dark matter decayed quickly, the gravitational effects would change, and we might see decay products. The fact that dark matter remains a dominant component today implies long lifetimes. Very slow decay is possible in some models, but the dominant component must persist across cosmic time. 8. The small-scale details are where the silhouette is least sharp. On small scales, inside dwarf galaxies, in satellite populations, in inner density profiles, there are debates and tensions that may involve baryonic physics, measurement uncertainties, or new dark matter physics. These are places where the next wave of observations and simulations may refine the picture. So we have strong evidence that something unseen contributes most of the gravitating matter. We can constrain its broad behavior, but we do not yet know its microscopic identity. That brings us to the boundary between evidence and search. If dark matter is a particle, we can try to detect its rare interactions in carefully shielded detectors deep underground. We can search indirectly for products of annihilation or decay in space. We can search at colliders for missing energy signatures. For now, we let the foundation settle, the evidence that points to a dominant, unseen matter component shaping the universe from early times to the present day. When we stand at the edge of what we can see, we have to learn a different kind of patience. Dark matter has been inferred from gravity in many places, but inference is not the same as identification. To identify something, we want to know what it is made of. We want to know the rules it follows. We want, if possible, to detect it interacting in a way that is repeatable, measurable, and not dependent on a single astrophysical interpretation. This is why dark matter is a bridge between astronomy and particle physics. Astronomy tells us that there is extra gravitating matter. Particle physics asks what kind of entity could exist, remain unseen, and still shape the universe. In this section, we will explore the most discussed candidate classes. We will not treat them all as equally likely. Instead, we will treat them as answers to a set of constraints. Each candidate survives because it can, in principle, satisfy the silhouette we described in Part 1. Non-baryonic, long-lived, cold, or effectively cold, and almost invisible to light. But we will also keep another rule close. A candidate is not a discovery. A candidate is a proposal. Many proposals can fit the known constraints. Only one, or perhaps more than one, can be real. So we will move slowly and carefully, with a quiet focus on what each candidate would predict and what it would take to confirm it. One of the reasons WIMPs became a central candidate class is that they emerged naturally from a simple cosmological idea. In the early universe, temperatures were so high that particle collisions were constant. If a new particle species existed and interacted with ordinary matter through forces of roughly weak strength, it would have been produced and destroyed in thermal equilibrium with the cosmic plasma. The particle number density would track the temperature like a quiet heartbeat of the early cosmos. As the universe expanded, it cooled. Densities dropped. Collisions became less frequent. Eventually, the interaction rate fell below the expansion rate, and the particle abundance stopped adjusting to equilibrium. The remaining population froze out, leaving a relic density that could persist for billions of years. The remarkable point is not that this mechanism proves anything, but that it can produce a relic abundance near the observed dark matter abundance for interaction strengths and masses that also appear in many extensions of particle physics. This rough coincidence is often called the WIMP miracle. It is a signpost, not a verdict. Still, it shaped the field, because it suggested dark matter might be accessible to experiments built with the same intuition that guides particle physics. Build a detector, reduce backgrounds, and look for rare interactions. A WIMP is a broad category, not a single particle. The key idea is that the particle is massive compared to ordinary neutrinos, and it interacts weakly enough that it does not glow, but strongly enough that it might occasionally scatter off an atomic nucleus, or, in some models, an electron. Why this is attractive is simple. It fits cold behavior. A heavy particle moves slowly compared to light once the universe cools. It fits non-baryonic. It is not made of protons and neutrons. It fits dark. It does not couple strongly to photons, and it offers multiple detection routes: direct detection, indirect detection, and collider searches. Many theoretical frameworks provide WIMP-like candidates. Some supersymmetric scenarios provide neutralinos. Some extra-dimensional ideas provide Kaluza-Klein excitations. Some simplified models describe a dark matter particle with a mediator that connects it to ordinary matter. But the important point is experimental. If WIMPs exist and have the right properties, we can attempt to detect them by building detectors that watch for nuclear recoils caused by rare collisions. We have been doing that for decades. And so far, we have not seen a confirmed signal. This does not mean WIMPs are impossible. It does mean the simplest and most strongly interacting versions have been pushed into narrower corners of parameter space. It also means that the phrase WIMP now contains a larger variety of ideas than it did in the early days of the search. Some WIMPs might interact primarily with leptons rather than nuclei. Some might have inelastic scattering that changes the recoil spectrum. Some might have momentum-dependent couplings. Some might be part of a larger dark sector, where the relic abundance is set by different processes than simple thermal freeze-out. Each of these variations changes what we should look for. Axions are a very different kind of candidate, and their appeal is also very different. Axions were originally proposed to solve a problem in the theory of the strong nuclear force, the strong CP problem. In simple terms, the equations allow a type of charge parity violation in the strong interaction that, if present at ordinary levels, would produce effects we do not observe. Axions emerge as a natural way to explain why that violation is so small. What makes axions special for dark matter is that, in many models, the same particle that solves the strong CP problem can also be produced in the early universe in such a way that it becomes cold dark matter. Unlike WIMPs, axions can be extremely light. Their coldness does not come from being heavy, but from being produced in a coherent field-like state with low momentum. Instead of thinking of axion dark matter as a swarm of particles bouncing around, we often think of it as a smooth, oscillating field permeating space, with an energy density that behaves like matter. Axions also have a very important experimental feature. They can couple, extremely weakly, to electromagnetism. In many models, axions can convert to photons in the presence of a strong magnetic field. This conversion is tiny, but if axions make up the dark matter halo, then a vast number of them pass through any laboratory volume, and the conversion rate, though small, might still be detectable with sensitive enough instruments. This has led to a family of experiments that feel, in a quiet way, like listening for a hidden radio station whose signal is almost buried in cosmic static. One famous approach is the haloscope, a resonant microwave cavity placed in a strong magnetic field. If axion dark matter passes through, it can convert into a photon with a frequency set by the axion mass. The cavity is tuned through frequencies, slowly scanning a range, searching for a narrow excess of power. The Axion Dark Matter Experiment, ADMX, is a leading haloscope effort. In a published search, ADMX reported results covering frequencies from about 1.1 to 1.31 gigahertz, corresponding to an axion mass range around 4.5 to 5.4 microelectron volts, with sensitivity reaching into plausible QCD axion model space in that range. There are other haloscope experiments as well, exploring different mass ranges and using different amplification techniques because the challenge changes with frequency. Higher axion masses correspond to higher photon frequencies and smaller cavities, which requires new engineering approaches. Again, we separate facts from hope. It is factual that axions are theoretically well-motivated and can form dark matter. It is factual that haloscope experiments can reach sensitivities to well-defined axion models in defined mass ranges. It is not factual that axions have been detected. That remains open. It is also common to discuss axion-like particles, which are similar in behavior but not necessarily tied to solving the strong CP problem. This broader family appears naturally in some theories beyond the standard model, including some versions of string theory, where multiple light fields can arise. Here, we need to be careful. The existence of axion-like particles is a theoretical possibility. Some may not be dark matter at all. Others could be. The important thing is that the experimental search strategies for QCD axions and axion-like particles can overlap, but the interpretation depends on the model. We can say confidently that axions and axion-like particles are plausible and testable. We cannot say confidently that they exist. That remains the question the experiments are designed to answer. Sterile neutrinos are another candidate class. The word sterile here means that they do not interact through the standard weak interaction the way ordinary neutrinos do. Instead, they interact only through mixing with ordinary neutrinos, making them extremely difficult to detect directly. Sterile neutrinos can be produced in the early universe and could form dark matter, particularly in the keV mass range. In that range, they can behave as warm dark matter, meaning their velocities can suppress the formation of very small-scale structures compared to cold dark matter. Warm dark matter is not ruled out, but it is constrained. The universe contains small galaxies and small-scale structure. The distribution of matter on small scales can be inferred from several probes, including the Lyman alpha forest, where absorption features in the spectra of distant quasars trace the distribution of intergalactic gas and, indirectly, the underlying matter power spectrum. If dark matter were too warm, it would erase small-scale structure that we do observe. Sterile neutrino dark matter also has a potential indirect signature: radiative decay producing an X-ray photon. This has motivated X-ray searches for faint spectral lines that might appear in dark, matter-dominated systems. Here we must be very clear. There have been claims in past years of unexplained X-ray lines at certain energies in certain astrophysical systems. The status of those claims has been debated, with alternative astrophysical explanations and instrumental concerns. No sterile neutrino dark matter signal is confirmed, so sterile neutrinos remain an option, but not a discovered one. Some dark matter models propose that the dark sector contains its own forces. One popular idea is a dark photon, a hypothetical gauge boson associated with a new U1 symmetry in the dark sector. If a dark photon exists, it could mix very weakly with the ordinary photon, allowing tiny interactions that experiments can search for. In some scenarios, a dark photon could be the mediator through which dark matter communicates with ordinary matter. In other scenarios, it might be part of a richer dark sector with multiple states. Hidden sector models can be extremely varied. Some involve dark matter that is itself charged under a dark force. Some involve multiple dark particles and dark radiation. Some include portal interactions that couple the dark sector to standard model particles through small mixing terms. At this point, the space of models becomes broad, so we keep our categories clear. The existence of a dark sector with additional forces is a plausible theoretical possibility. Specific details, such as the strength of mixing, the masses of dark particles, and their cosmological history, are model-dependent. Many of these ideas remain speculative until constrained or supported by experiments. Self-interacting dark matter is not one particle candidate. It is a property that can be realized in many models. The motivation is connected to small-scale structure. If dark matter particles scatter off each other, even rarely, this can redistribute energy and flatten dense central cusps into cores in dwarf galaxies, potentially addressing some observational tensions. On the other hand, cluster-scale observations constrain how strong these self-interactions can be at higher velocities. A consistent self-interacting model often requires velocity-dependent interactions, stronger at dwarf galaxy velocities, weaker at cluster velocities. This is a vivid example of how astrophysical observations and particle properties connect. The same dark matter particle can behave differently in different environments if its interaction strength depends on relative speed. But, again, we keep the boundary. Self-interacting dark matter is a motivated and actively studied possibility. It is not confirmed. What would count as confirmation for a particle candidate? Because the candidate space is broad, it helps to state what we would accept as a convincing identification. A convincing discovery would have some combination of these features. A clear signal in a laboratory detector that matches a specific particle interaction model. Reproducibility across independent experiments with different target materials and backgrounds. Consistency with astrophysical constraints and cosmological abundance. If indirect signals are involved, correlation with expected dark matter distributions, and consistency across multiple targets. If collider signals are involved, a consistent mediator framework that links collider data to cosmology. In practice, the most compelling future would be a convergence, a direct detection signal with a compatible indirect signature, and perhaps collider evidence of a related mediator. This is a high standard. But the history of physics shows that when something is real and measurable, multiple methods eventually begin to agree. Now that we have surveyed the candidate landscape, we can move into the search strategies. We begin with the most direct approach, listening for dark matter to touch ordinary matter in a detector designed to be quieter than the deep underground itself. Imagine building a machine that listens for a single, tiny nudge, not a loud crash. Not a shower of particles in a high-energy collider. A single recoil in a quiet medium, shielded from as much noise as the Earth can block. That is the spirit of direct detection. The basic idea is simple. If dark matter is made of particles that pass through the Earth, then billions of them flow through us every moment. The reason we do not notice is that if they interact at all, they do so extremely rarely. Direct detection experiments try to catch one of those rare interactions. In many models, the interaction is a collision between a dark matter particle and an atomic nucleus. The nucleus recoils, producing a small amount of energy in the form of scintillation light, ionization, or phonons, depending on the detector material. Because the signals are small and rare, the central challenge is background. Cosmic rays, natural radioactivity in detector materials, neutrons produced by muons, radioactive isotopes in the environment, and even neutrinos from the sun can all produce events that mimic or obscure dark matter signals. So direct detection is, in practice, the art of eliminating backgrounds. Cosmic rays constantly bombard the Earth. At the surface, their rate is high enough to flood a sensitive detector with noise. By placing detectors deep underground, under kilometers of rock, we reduce the cosmic ray muon flux dramatically. The rock acts as a shield. Even underground, experiments use additional shielding: water tanks, polyethylene, lead, and active veto systems that detect and reject events associated with muons or other backgrounds. Every layer is an attempt to turn the loud universe into a whispering room. Over time, several detector technologies have become central. Noble liquid time projection chambers, especially those using xenon, have become some of the most sensitive detectors for WIMP-like dark matter. They work by measuring two signals: a prompt scintillation flash and a delayed ionization signal. The ratio between these signals can help distinguish nuclear recoils from electron recoils, which are a common background from gamma rays and beta decays. This discrimination is not perfect, but it provides a way to statistically separate classes of events, and it is one reason xenon time projection chambers scale well to large masses. Cryogenic crystal detectors measure phonons and ionization in ultra-cold materials. Because they operate at very low temperatures, they can detect very small energy deposits and are strong in searches for low-mass dark matter. In that lower mass regime, the recoil energies from nuclear scattering can be extremely small, and the technical challenge becomes how to detect energy deposits that are barely above the thermal noise. Scintillating crystal experiments, such as those using sodium iodide, have focused on annual modulation signals. The idea that the dark matter flux should vary slightly over the year due to the Earth's motion around the Sun, combined with the Sun's motion through the galaxy. Each approach has strengths and weaknesses, and the field benefits from diversity because different detector materials respond differently to potential dark matter interactions. To make the logic vivid, consider a two-phase xenon detector. A particle interacts in liquid xenon and produces a prompt flash of ultraviolet scintillation light. The same interaction also frees electrons. An electric field drifts those electrons upward into a gas layer, where they produce a second burst of light through electroluminescence. The time difference between the two signals tells us the depth of the interaction. The light pattern across sensors tells us the horizontal position. This allows three-dimensional event reconstruction. That matters because the cleanest region of the detector is often the inner fiducial volume, where backgrounds from detector walls are reduced. By selecting events from the inner region, experiments reduce contamination. These detectors also calibrate carefully, using known sources to characterize how nuclear recoils and electron recoils appear in the signal space. The separation is a form of learned pattern, grounded in controlled data. The large xenon detectors have reached extraordinary sensitivity. The LUX Zeppelin experiment, often called LZ, is one of the leading xenon time projection chamber efforts. Recent LZ results have reported no evidence of WIMPs and have set world-leading limits on the spin-independent WIMP nucleon cross-section. In combined analyses of science runs, the minimum excluded cross-section is around 2.2 times 10 to the minus 48 square centimeters for a WIMP mass around 43 GeV divided by c squared. Under the stated confidence assumptions, XENONnT is another major xenon experiment. In its first published nuclear recoil search, XENONnT reported no significant excess of nuclear recoil events in the analyzed energy range and set an upper limit on the spin-independent WIMP nucleon cross-section with a minimum around 2.58 times 10 to the minus 47 square centimeters for a WIMP mass around 28 GeV divided by c squared at 90% confidence level within the analysis framework described in its publication. PandaX 4T, a xenon experiment, has also produced competitive limits. A reported minimum excluded spin-independent cross-section is around 1.6 times 10 to the minus 47 square centimeters for a WIMP mass around 40 GeV divided by c squared under its analysis assumptions. These numbers are not just technical trophies, they are information about nature. They tell us that if WIMPs exist in the tens of giga-electron-volt mass range with spin-independent couplings to nuclei, those couplings must be extremely small, below levels once considered natural in many models. They also tell us that future progress is harder, because as we approach extreme sensitivities, new backgrounds and systematics begin to matter. Not all WIMP interactions are spin-independent. Some models predict spin-dependent couplings, where the interaction depends on the spin of the nucleus. Different target materials and isotopes have different sensitivity to these couplings. This is one reason multiple experiments and target choices are valuable. Some models also predict interactions with electrons rather than nuclei, especially for lighter dark matter candidates. In that case, the experimental signature changes. Instead of nuclear recoil energies, we look for tiny ionization signals and low-energy electron recoil patterns. This diversity is important. A null result in one channel does not rule out all channels. As direct detection experiments grow more sensitive, they begin to encounter a new background: neutrinos. Neutrinos from the Sun, from the atmosphere, and from distant supernovae can scatter off nuclei and produce recoils. This background is irreducible in the sense that neutrinos are real and penetrate shielding. The term neutrino floor is often used to describe the sensitivity level where neutrino backgrounds become significant, making it more challenging to distinguish dark matter signals from neutrino-induced recoils. But it is not a hard wall. There are strategies to move beyond it: directional detectors that can measure the direction of recoils, statistical separation using multiple targets, and improved background modeling. The floor is more like a region where the search becomes more subtle and requires new techniques. Some dark matter searches have focused not on a one-time event rate, but on a seasonal pattern. The Earth orbits the Sun. The Sun moves through the Milky Way. If dark matter forms a roughly stationary halo in the galactic frame, then the Earth's speed relative to that halo changes slightly over the year. In simple models, this could produce a small annual modulation in detection rates. The DAMA/Libra experiment, using sodium iodide crystals, has reported an annual modulation signal and has interpreted it as evidence of dark matter. However, this interpretation remains contested, because other experiments using similar target materials and improved background controls have not confirmed a compatible modulation signal under the same assumptions. For example, ANIAS has reported results compatible with the absence of modulation and has discussed tension with the DAMA/Libra interpretation at stated sensitivity levels. This situation is not resolved by argument. It is resolved by data. The way forward is continued measurement, improved detectors using the same target material, and careful control of environmental and systematic effects, such as temperature, radon, and detector stability. The broader lesson is that dark matter searches require extraordinary caution. When signals are subtle, the line between discovery and background effect can be thin. Direct detection is not only a WIMP program. Some experiments look for dark matter that is so light that nuclear recoils are too small to detect efficiently. These experiments may target electron recoils, use superconducting devices, or search for absorption of bosonic dark matter such as dark photons or axion-like particles. Other searches look for daily modulation or directionality, because directional information would strongly distinguish dark matter from isotropic backgrounds. The field is expanding because the candidate space is expanding, and the deeper reason is this. The absence of a clear WIMP signal has encouraged a wider search, not a retreat. Now we move to a different approach. If dark matter does not collide with us often, perhaps it reveals itself by its rare self-annihilations or decays in space, producing gamma rays, cosmic rays, or neutrinos. Or perhaps it is produced at high energy in colliders, escaping detectors and leaving behind missing energy. These are the indirect and collider routes. Indirect detection is a search for the byproducts of dark matter physics in the sky. If dark matter particles can annihilate with each other, or decay, they could produce standard model particles, gamma rays, electrons and positrons, antiprotons, neutrinos, or other detectable messengers. The challenge is that the sky is full of other processes that produce the same messengers. Pulsars produce gamma rays and positrons. Supernova remnants accelerate cosmic rays. Black hole jets and star-forming regions glow across the spectrum. Even diffuse galactic emission can create features that resemble new physics if we are careless. So, indirect detection is, in practice, an exercise in separating potential dark matter signals from astrophysical foregrounds and backgrounds. This is difficult, but it is also powerful, because it can probe dark matter in environments we cannot replicate on Earth. High-density regions, large volumes, and long timescales. One of the cleanest indirect targets is the dwarf spheroidal galaxies that orbit the Milky Way. These systems are believed to be dark matter-dominated, with low gas content and low ongoing star formation. That means fewer astrophysical processes that produce gamma rays. In principle, this makes them clean laboratories, high dark matter density, low background. The Fermi Large Area Telescope, often called Fermi-LAT, has observed many dwarf spheroidals over long periods. Analyses combining multiple dwarf galaxies have produced strong constraints on dark matter annihilation cross-sections for certain channels, especially in the GeV mass range. A key reason these analyses are valued is that they use many targets. A single dwarf could have uncertainties in its dark matter density profile, but a population of dwarfs, analyzed together, can produce a more robust statistical constraint. Fermi-LAT analyses with long exposures, including studies using around 14 years of data in the modern era, continue to refine limits and explore the parameter space where a thermal relic annihilation cross-section might be detectable depending on mass and final states. These studies have not produced a universally accepted dark matter detection. Instead, they have placed limits that help narrow the range of viable models. This is a pattern we will see often. Null results are not silence, they are information. Another prominent target is the center of the Milky Way, where dark matter density is expected to be high in many models. However, the galactic center is also one of the most complex astrophysical regions in the sky. It contains many gamma-ray sources, diffuse emission, cosmic ray interactions with gas, and unresolved populations of objects. There have been discussions in the scientific literature about excess emissions in the galactic center region and whether they could be explained by dark matter annihilation or by unresolved astrophysical sources such as millisecond pulsars. At present, there is no consensus that a dark matter interpretation is required. The astrophysical backgrounds are complex enough that caution is essential. So dwarf galaxies remain among the most conservative targets because their backgrounds are simpler. Dark matter annihilation or decay could produce cosmic ray signatures, such as an excess of positrons or specific spectral features in antiprotons. But cosmic rays propagate through the galaxy, scattering and diffusing in magnetic fields. Their spectra are shaped by source distributions, propagation models, and solar modulation. This introduces uncertainties that can be large compared to the subtle signals we are searching for. Therefore, Cosmic ray hints are intriguing but often ambiguous. They can motivate certain models, but they rarely close the case on their own. Neutrinos offer another route. If dark matter scatters off nuclei, it could lose energy and become gravitationally captured by massive bodies like the Sun. Over time, captured dark matter could accumulate in the Sun's core and annihilate, producing neutrinos that escape and can be detected by neutrino telescopes. This idea links direct detection and indirect detection. The same scattering that would produce nuclear recoils in a detector could also allow capture in the Sun. Neutrino telescope searches for an excess from the Sun have placed constraints on certain dark matter models, particularly for spin-dependent interactions where solar capture can be efficient. Again, the results so far are constraints, not detections. Particle colliders provide a different style of test. If dark matter can be produced in high-energy collisions, it would not be detected directly, because it would pass through the detector without interacting much. But it would carry away energy and momentum. We can infer this as missing transverse energy, an imbalance in the measured momentum of visible particles in the plane perpendicular to the beam. Collider searches often look for events where something visible recoils against something invisible, such as a jet plus missing energy, or a photon plus missing energy, or a Z boson plus missing energy. The interpretation depends on the theoretical framework. What mediator connects dark matter to standard model particles, what its mass is, and what couplings it has. Collider constraints can be translated into limits on dark matter interactions, but those translations require assumptions. This is why the particle physics community often presents results in simplified models that make the assumptions explicit. Collider searches have not produced a confirmed dark matter discovery, but they have constrained mediator scenarios and helped map the ways dark matter could interact with ordinary matter, especially for lighter mediators and certain coupling patterns. It helps to see direct detection, indirect detection, and colliders as three ears listening for the same quiet voice. Direct detection listens for a whisper of contact with nuclei or electrons in a shielded detector. Indirect detection listens for the faint aftermath of annihilation or decay in the sky. Colliders listen for missing energy that suggests invisible particles were produced. If dark matter interacts through a specific mediator, these methods can be linked. But the links are not automatic. Some models predict strong direct detection signals and weak collider signals. Some predict the opposite. Some predict indirect signals only in specific environments or only for certain channels. This is why the search program is broad. We do not know which door dark matter will walk through, if it walks through any door we have built so far. And that brings us to a deeper question. What if the dark matter we infer is not a new particle at all? What if it is made of compact objects? Those possibilities are not the mainstream explanation, but they are important to address, because any complete story must also show why alternatives are constrained and where uncertainties remain. In Part 3, we will explore compact object possibilities and then step into the open questions and the future. For now, we let Part 2 settle. We have walked through the candidate landscape and the search strategies. We have seen that the experiments have become unbelievably sensitive. We have seen that the absence of a clear signal has already reshaped which ideas look most plausible. And we have seen that the next phase of the search will likely depend on both deeper instruments and new ways of reading the universe's quiet clues. There is a quiet temptation in science that comes whenever we face something unseen. If we cannot see the missing mass, perhaps it is not a new kind of particle at all. Perhaps it is ordinary matter that is simply hard to detect. Perhaps it is hidden in cold objects, faint objects, compact objects. Perhaps the missing mass is not missing. Perhaps our description of gravity is incomplete. To tell the dark matter story honestly, we need to walk through these possibilities with care. Not to inflate them beyond what the evidence supports, and not to dismiss them without understanding what they can and cannot explain. We begin with the most intuitive alternative. Maybe dark matter is made of familiar stuff that simply does not shine. Ordinary matter is baryonic matter. Protons, neutrons, electrons, atoms, molecules, dust, planets, rocks, gas clouds, stars, and stellar remnants. Much of baryonic matter is dark in the everyday sense. Cold gas in the outer parts of galaxies can be difficult to detect. Dust can hide starlight. Compact remnants like black holes and neutron stars do not glow brightly unless they accrete material. So early in the history of the missing mass problem, it was natural to ask whether the missing mass could be baryonic matter in dim or compact forms. But we have strong constraints on the total baryon budget. Big Bang nucleosynthesis and the cosmic microwave background constrain the density of baryons in the universe. Those constraints are consistent with each other and indicate that baryons are a minority component of the total matter density. In other words, even if every baryon were hidden from our telescopes, there would still not be enough baryonic mass to account for the full dark matter requirement inferred from cosmology. This is one of the strongest reasons the mainstream view is that dark matter is non-baryonic. However, it does not eliminate compact objects as a partial contributor. Even if baryons cannot make up all of dark matter, compact objects could still be present in significant numbers, and their presence matters for astrophysics and for certain observational signatures. MACHO is an older term that means massive compact halo object. It refers to compact bodies in galactic halos that could contribute to the gravitational mass but emit little light. Examples include brown dwarfs, faint low-mass stars, white dwarfs, neutron stars, black holes, even free-floating planets. If large numbers of such objects existed in the halo, they would increase the halo's mass without adding much light. But we can test this idea with gravitational microlensing. Microlensing occurs when a compact object passes in front of a background star. The compact object's gravity bends light, creating a temporary brightening of the star. The light curve shape and timescale carry information about the lens mass and relative motion. Microlensing surveys have monitored millions of stars to look for these events and have used the event rates to constrain how many compact objects can exist in certain mass ranges. The broad conclusion from decades of microlensing work is that compact objects cannot make up all of the dark matter across a wide range of masses. The exact limits depend on assumptions about halo models and the lens population, but the key point is that if the halo were dominated by compact objects of many masses, we would expect more microlensing events than are observed. This strongly restricts the MACO explanation for the majority of dark matter. But then the story takes a turn. Primordial black holes, often abbreviated as PBHS, are black holes that could have formed in the very early universe, before stars existed. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes could form from the collapse of overdense regions shortly after the Big Bang, under certain conditions. These conditions could be related to density fluctuations, phase transitions, or other early universe physics. If primordial black holes formed early enough, they would not be baryonic in the same sense as ordinary matter. They would not be constrained by the baryon density in the same way, because their formation can occur before nucleosynthesis in some scenarios. This makes PBHS conceptually attractive as a dark matter candidate class. Dark matter made of gravity itself, in the form of black holes, without requiring a new particle species. But PBHs are not a free solution. They face many constraints, and those constraints are strong across many mass ranges. PBHS can be constrained by several kinds of observations. Microlensing. Compact objects in certain mass ranges produce detectable microlensing events in surveys monitoring stars in the Milky Way, the Magellanic Clouds, and other fields. Dynamical effects. A population of massive compact objects would heat stellar systems, disrupt wide binary stars, and alter the structure of star clusters. Accretion signatures. PBHS could accrete gas and emit radiation, potentially affecting the cosmic microwave background or producing radio and X-ray signals, depending on uncertain accretion physics. Gravitational waves. Mergers of black holes produce gravitational waves, and the merger rates and mass distributions can constrain PBH populations, though interpretation depends on astrophysical black hole formation channels as well. A key modern example of microlensing constraints comes from the OGLE survey. Analyses of microlensing events have been used to set upper limits on the fraction of dark matter that can be in PBHS in certain mass ranges, including very low masses in the Earth to Jupiter regime and higher masses in other analyses. The details depend on the field observed and the modeling of known lens populations, but the overall message is that PBHs cannot make up all dark matter in many mass ranges. Reviews of PBH dark matter, such as those summarizing recent developments, emphasize that constraints cover most of the mass spectrum, leaving only limited windows where PBHS could still contribute a significant fraction of dark matter. We should be careful with how we speak about these windows. When people say there are allowed windows, they usually mean less constrained regions. The constraints are complex and sometimes dependent on assumptions about astrophysical populations and early universe physics. A window is not a guarantee. It is a region where the question is not yet fully closed. Speculation. It remains logically possible that PBHs could make up most or even all dark matter if they occupy a mass window that is less constrained, and if the underlying assumptions in various constraints shift in ways that allow it. However, the mainstream view in the research literature is that it is difficult for PBHs to constitute all dark matter across the full range of observational constraints, and many studies find strong exclusions in mass ranges that would otherwise be attractive. That is a careful way to say it. PBHS are interesting. PBHS are testable. PBHS are not confirmed. Another class of alternatives changes the gravitational law. If the motions of stars and galaxies do not match the visible mass, perhaps gravity behaves differently on certain scales or at certain accelerations. Modified Newtonian dynamics, often abbreviated MOND, is a famous example of a framework that adjusts dynamics at low accelerations to reproduce galaxy rotation curves with less need for dark matter in some contexts. There are also relativistic extensions designed to address lensing and cosmology, because any alternative must reproduce not only galaxy rotation curves, but also gravitational lensing, cluster dynamics, the CMB anisotropy peaks, and large-scale structure growth. This is where the alternative gravity story becomes difficult. Dark matter does not only appear in galaxy rotation curves, it appears in clusters, in the CMB, in the growth of structure, and in lensing maps. Any modified gravity theory that aims to replace dark matter must reproduce this full network of evidence. Cluster collisions, such as the bullet cluster, have been widely discussed in this context because lensing maps show gravitational potential peaks separated from the hot gas, which contains much of the baryonic matter in clusters. In the standard dark matter interpretation, this is naturally explained by collisionless dark matter, halos passing through while gas is slowed. Some modified gravity models attempt to reproduce aspects of this behavior, but many still require some additional unseen mass component at cluster scales, which reintroduces a dark component in a different form. So the state of the field is roughly this. Modified gravity ideas can be effective at describing certain galactic scale regularities. They face challenges in clusters and cosmology, and many versions require additional components. Dark matter as a matter component remains the standard explanation because it fits many independent lines of evidence within one consistent cosmological framework. That does not mean modified gravity research is worthless. It means the bar is high. When the evidence is broad, the alternative must be broad as well. So what do we learn from these alternatives? First, baryonic matter cannot make up all dark matter because cosmology constrains the baryon budget. Second, compact objects such as macros are strongly constrained by microlensing and dynamics, so they cannot be the dominant explanation across broad mass ranges. Third, primordial black holes remain interesting because they can be non-baryonic and early formed, but they face many constraints that restrict how much of dark matter they can explain, depending on mass. Fourth, modified gravity can describe some aspects of galactic dynamics, but must confront the full network of evidence, including the early universe and lensing in complex systems. These alternatives matter because they sharpen the main argument. They show that the dark matter hypothesis is not adopted because it is fashionable. It is adopted because it is, so far, the simplest consistent way to explain a large set of observations with one additional ingredient, an unseen matter component. Now we step into the question that makes the story live. If dark matter is real, and most of the universe's matter is made of it, why have we not identified it yet? And what are we about to learn next? We know dark matter is there in the sense that gravity behaves as though it is there. We know it shaped the cosmic microwave background. We know it helped seed the cosmic web. We know galaxies sit inside halos. We know clusters are dominated by unseen mass. We know lensing can map its distribution, but we do not know the identity of the dark matter. We do not know whether it is one particle or multiple components. We do not know whether it has self-interactions beyond gravity. We do not know whether it has tiny electromagnetic couplings through portals. We do not know its mass scale. We do not know its production history in detail. So in this final section, we will make the unknowns concrete. Then we will look forward at what could be next, meaning what experiments and surveys are likely to reshape the landscape soon. Question 1. Is dark matter one thing or many? The standard cosmological model often treats dark matter as one cold component. That is a modeling choice that fits large-scale data well. But nature is not obligated to be simple. Dark matter could be a mixture, part particle, part compact object, or multiple particle species with different masses and interactions. Some fractions could be warm, others cold. Some could interact in a dark sector, others could be almost purely gravitational. At present, we do not have evidence that requires multiple components, but we also do not have evidence that forbids them. Many models in the literature explore mixed scenarios because they can relieve certain tensions or produce richer phenomenology. We label the key boundary. Fact: current data are well described by a dominant cold dark matter component on large scales. Speculation: dark matter could include multiple components that are not yet resolved by existing observations. Question 2. How cold is dark matter, really? Cold dark matter is a cosmological phrase. It means that on the scales relevant for structure formation, the dark matter is non-relativistic, early enough that it can clump on small scales. But there is room for nuance. Warm dark matter, such as certain sterile neutrino scenarios, can suppress structure on the smallest scales. Observationally, the small-scale power spectrum is constrained by the existence of small galaxies and by probes like the Lyman alpha forest. These constraints tend to push the dominant component toward being effectively cold, but the exact boundary depends on model assumptions and astrophysical uncertainties. What is likely is that if the dominant component is warm, it is not extremely warm. And if there is a warm component, it may be a subcomponent rather than the whole. Again, we keep it clean. Fact: large-scale structure and early universe data strongly favor a dominant component that behaves cold in structure growth. Speculation: a subcomponent could be warmer without violating current constraints. Question 3. Do halos have cores or cusps? And what does that mean? On the smallest scales, there are debates about inner halo density profiles. Cold dark matter simulations with only dark matter often produce cuspy inner profiles, where density rises steeply toward the center. Some observed dwarf galaxies appear to prefer cored profiles, with flatter central densities. There are two broad explanations. 1. Baryonic feedback. Star formation and supernova explosions can move gas around and change the gravitational potential, potentially heating dark matter and flattening cusps into cores. The effectiveness of this depends on how much star formation occurred and how energy couples to the dark matter distribution. 2. New dark matter physics. Self-interacting dark matter can also produce cores by redistributing energy through scattering, especially in low-velocity environments like dwarf galaxies. The truth may be a combination. Some galaxies may be shaped primarily by baryonic processes. Some may reveal dark matter physics. Some observational inferences may change as data improve. This is one reason small-scale structure remains an active area. The small-scale problems of cold dark matter are not a single problem. They are a cluster of puzzles at the intersection of astrophysics, simulations, and measurement. Question 4. Does dark matter self-interact? We have evidence that dark matter behaves as collisionless in many environments, especially on cluster collision scales. But collisionless in this context means not strongly collisional. It does not mean no interactions at all. Self-interacting dark matter models propose a scattering cross-section per unit mass that can be small enough to satisfy cluster constraints but large enough to affect dwarf galaxy cores. In the literature, some simulations have shown that certain self-interaction strengths can produce cores and other features consistent with some observed dwarves. Other work explores velocity-dependent interactions to reconcile constraints across scales. This area is active because it is testable. If dark matter self-interacts, it can alter halo shapes, subhalo survival, and core sizes. These can be compared to lensing data, stellar kinematics, and satellite populations. But it remains uncertain because astrophysical processes can mimic some of the same effects. So we keep our categories. Fact: dark matter cannot have large self-interactions that would cause strong drag in cluster collisions under standard interpretations. Speculation: dark matter could have moderate velocity-dependent self-interactions that affect small-scale structure while remaining consistent with cluster constraints. Question 5. Why has direct detection not found it yet? This question can feel emotional because it is about expectations. For many years, it was reasonable to hope that WIMPs would be discovered as detector sensitivities grew. The experiments became sensitive enough to test the thermal relic scale in certain models, and still, the detectors did not see a clear signal. What could this mean? Possibility. 1. Dark matter is not a WIMP in the mass and coupling ranges targeted so far. Possibility 2. Dark matter is a WIMP, but its interaction with nuclei is weaker than expected, or it interacts through channels that are less visible to current detectors. Possibility 3. Dark matter is lighter than the typical WIMP range, making nuclear recoil detection harder and pushing the search toward electron recoil channels and new technologies. Possibility 4. Dark matter is heavier, or interacts in ways that produce signals outside the standard analysis windows. Possibility 5. Dark matter is a field-like particle, such as an axion, rather than a scattering particle in the WIMP sense, making the search methodology different. Possibility 6. Dark matter is not a particle at all, but a compact object population, though, as we discussed, that faces strong constraints. The important point is that the null results are informative. They shape which possibilities remain plausible. Dark matter is not only a laboratory question, it is also an observational question. The next decade is bringing powerful new surveys and space missions that will map the universe with a precision that makes weak lensing and cosmic structure measurements sharper than ever. The Euclid mission, led by the European Space Agency, is designed to map the geometry of the dark universe. It does this in part by measuring the shapes of vast numbers of galaxies to infer weak gravitational lensing, which traces the distribution of matter, including dark matter, along the line of sight. Weak lensing is subtle. It requires careful control of instrumental effects, shape measurement biases, and photometric redshift uncertainties. But the reward is enormous. A large-scale map of matter clustering and its evolution over cosmic time, Euclid has begun releasing datasets and has already identified many strong lens candidates in early data releases, while the full survey aims to cover a large fraction of the sky and observe a vast number of galaxies. What will Euclid do for dark matter? It will not detect a particle in a detector, but it will constrain the clustering of matter, the shape of the matter power spectrum, and potential deviations from the standard model that could hint at warm, dark matter or other physics. It will also provide a large sample of strong lenses and weak lens measurements that can test halo substructure. That is where particle physics can enter. Different dark matter models predict different small-scale substructure patterns. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, often called LSST, is designed to survey a vast area of the sky repeatedly over about a decade. This repeated imaging turns the sky into a movie. For dark matter, Rubin's wide and deep imaging will enable precision weak lensing measurements and large-scale structure studies. It will also find and monitor countless transient events and variable objects, improving distance measurements and cosmological constraints that indirectly tie into dark matter and dark energy. Rubin's strength is not just depth, but cadence and uniformity. By revisiting the same sky again and again, it builds an extraordinary data set with both spatial and temporal information. This matters for lensing systematics as well. Repeated observations help average out atmospheric and instrumental noise and provide multiple measurements of galaxy shapes. The Nancy Grace Roman Space Telescope is designed to conduct wide-field infrared surveys from space. Because it operates above the atmosphere, it can provide stable, sharp imaging, which is valuable for weak lensing shape measurements. Roman will investigate dark matter through weak lensing and through the study of gravitational lenses. It is expected to find many strong lenses, which can be used as laboratories for dark matter substructure. Small perturbations in lensed images can reveal the presence of subhalos, allowing tests of the small-scale distribution of dark matter. Space-based imaging also helps with photometric redshifts and galaxy morphology measurements, which support cosmological inference. Together, Euclid, Rubin, and Roman form a kind of complementary trio. A wide space survey, a deep time domain ground survey, and a sharp space-based wide field program. Their combined data will tighten constraints on how matter clusters and how small-scale structures behave. While the sky is being mapped, underground detectors continue to grow. The near-term story in direct detection is continued exposure and incremental improvements in background control and analysis. The longer-term story is next-generation detectors with larger masses and improved sensitivity, approaching the region where neutrino backgrounds become the dominant challenge. As the detectors become larger, the experiments also become multipurpose observatories for rare events, solar neutrinos, supernova neutrinos, and other physics. This can be seen as a quiet advantage. Even if dark matter remains elusive, the instruments still advance fundamental physics. In the WIMP search space, the lack of detection is pushing experiments to explore lower masses, different interaction operators, and new detection materials. In the axion search space, the story is one of scanning. Haloscope experiments like ADMX scan frequency bands carefully. New technologies aim to widen the bandwidth, scan faster, and reach higher frequencies corresponding to higher axion masses while maintaining sensitivity. There are also helioscope experiments that search for axions produced in the Sun, as well as laboratory searches for axion-like particles using magnetic fields and precision electromagnetic systems. Each method probes different couplings and different parameter regions. If dark matter is discovered in the coming years, what might the discovery look like? It could look like a cluster of consistent events in an underground detector, producing a recoil spectrum and modulation pattern that cannot be explained by known backgrounds. Then, another detector with a different target material could see a compatible signal, and the two together could point to a mass and cross-section range. It could look like a narrow spectral line in an axion haloscope scan that persists, follows the expected behavior under tuning, and is independently reproduced by another haloscope, linking the signal to a specific axion model. It could look like a new particle mediator in collider data, with missing energy signatures and decay patterns that connect to direct detection expectations, though the cosmological connection would still require careful modeling. It could look like an indirect signal seen consistently across many dark matter-dominated environments, with a morphology that follows dark matter distributions rather than astrophysical populations, and with spectral features consistent across instruments and analyses. Or it could be subtler. It could be a pattern in the small-scale structure of halos that points to warm dark matter or self-interactions, which then guides particle searches toward a narrower theory space. In reality, the first moment of discovery may not feel dramatic. It may feel like repeated checks, consistency tests, the quiet reduction of uncertainty, a signal that refuses to go away. And only then, after months or years of scrutiny, it becomes real. The deepest unknown. Why does dark matter exist? There is one question behind all the others. Why does the universe contain dark matter at all? If dark matter is a particle, why was it produced in the early universe in just the right abundance to shape structure and still remain today? Why does it interact so weakly with ordinary matter? Why does it appear to be stable on cosmic timescales? If dark matter is a field, why does that field exist, and why does it have the mass and couplings it has? These are questions that point toward deeper theories, perhaps toward symmetries, perhaps toward hidden sectors, perhaps toward the structure of quantum fields in the early universe. We cannot answer them yet, but we can describe what progress would look like. Progress would look like measurement. Measurement would look like identification. Identification would look like a model that connects cosmology, astrophysics, and particle physics in one consistent story. So, what do we know? What do we not know? And what could be next? We know that the universe behaves as though most of its matter is invisible. We know that this invisible component shaped the early universe and still shapes galaxies and clusters today. We know that it is not mostly baryonic. We know that it is cold or effectively cold on large scales. We know that it is distributed in halos and the cosmic web. We know that it is difficult to detect directly, which implies very weak interactions with ordinary matter and light, at least in the ways we have searched so far. We do not know its identity. We do not know whether it is one particle, multiple particles, or something else entirely. We do not know its mass scale. We do not know whether it self-interacts in subtle ways. We do not know whether it has hidden forces. We do not know whether the small-scale puzzles are telling us something profound about dark matter physics or something profound about galaxies. And what could be next is a widening of our senses. New maps of lensing and structure from Euclid, Rubin, and Roman. New underground detectors reaching deeper into rarer interactions. New axion searches scanning wider ranges with better sensitivity. New theoretical work connecting the dots between what the sky reveals and what particle physics permits. In science, mysteries are not solved by hope. They are solved by persistence. And dark matter, for all its silence, has already changed how we see the universe. Because once you accept that most matter is invisible, the night sky changes. The bright galaxies become tracers. The light becomes a surface marker. And beneath it, the mass, quiet, heavy, unseen, forms the real architecture of the cosmos. If you want more calm, deeply researched space stories told in this relaxed style, please like the video, subscribe to Early Science, and turn on notifications so you don't miss the next one. Before we end, it helps to spend time with a simple truth. Dark matter is not invisible because it is irrelevant. Dark matter is invisible because it reveals itself through gravity, and gravity leaves traces in shapes, speeds, and patterns. If you want to understand why scientists are so confident that something is there, even without a particle in hand, it helps to understand the main ways we infer dark matter's presence. Think of this section as a gentle walk through the methods, not a technical lecture, just a calm tour of the evidence, the tools, and the places where uncertainty still lives. Gravitational lensing is one of the most direct ways to map mass, including mass we cannot see. The idea comes from general relativity. Mass and energy curve space-time, and light follows that curvature. When light from a distant galaxy passes near a massive object, the path bends. Sometimes the effect is dramatic. Arcs, rings, multiple images. That is strong lensing. But most of the time, the effect is subtle. A distant galaxy's apparent shape becomes slightly stretched or sheared. No single galaxy tells you much because galaxies have many intrinsic shapes. But if you measure millions of galaxies, statistical patterns emerge, and you can infer the distribution of intervening matter. That is weak lensing. Weak lensing does not just tell us that dark matter exists. It tells us where matter is. It maps the cosmic web, filaments, nodes, and the distribution of halos. There is a quiet elegance here. Stars and gas can be messy. They can heat, cool, form structures, explode, and swirl. But lensing, if measured carefully, responds to mass itself. That is why missions and surveys designed for weak lensing, Euclid, Rubin, Roman, are so important. They are, in a sense, measuring the universe's mass distribution using light as a probe. Yet lensing is also challenging. To measure weak lensing, you must correct for the instrument's point spread function, detector effects, atmosphere for ground-based surveys, and subtle biases in shape measurement. You must estimate galaxy redshifts, often photometrically, and account for uncertainties. You must validate the pipeline with simulations. When you see a beautiful colored dark matter map in the news, it is worth remembering. Behind that map is a long chain of careful calibration. The map is real, but it is also the output of a method that must be controlled precisely to be trusted. Rotation curves were one of the earliest and most intuitive pieces of evidence for dark matter. If most mass in a galaxy were concentrated where the light is, stars in the central region, then the orbital speed of stars and gas should decline with distance at large radii. In the same general way, planets farther from the Sun orbit more slowly. But in many spiral galaxies, measured rotation curves stay flat far out into the disk. The orbital speeds do not fall as expected based on visible mass alone. This implies either that mass continues to increase with radius, or that gravity behaves differently on those scales. The standard interpretation is that galaxies sit in extended halos of dark matter. The luminous disk is embedded in a much larger mass distribution. Rotation curves are still important today, but they are not the whole story. They are part of a pattern that repeats. Dynamics indicate more mass than we see. In galaxies, that appears as flat rotation curves. In clusters, it appears as high galaxy velocity dispersions and hot X-ray gas temperatures that require deep gravitational potential wells. In lensing, it appears as gravitational potential maps that exceed visible mass. In cosmology, it appears as the need for a non-baryonic component to match the CMB and structure formation. The cosmic microwave background, the afterglow of the early universe, encodes dark matter in its pattern of temperature anisotropies and polarization. In the early universe, before recombination, ordinary matter and photons formed a tightly coupled plasma. Gravity tried to compress regions of higher density, while radiation pressure pushed back. This created acoustic oscillations, waves in the plasma. Dark matter, if it does not couple to photons, behaves differently. It can begin clumping earlier and provides gravitational wells that shape the oscillations. The result is that the CMB power spectrum, the pattern of peaks and troughs, depends on the densities of baryons and dark matter. When missions like Planck measure the CMB with high precision, they allow constraints on parameters such as the dark matter density and baryon density. This is one of the reasons dark matter is not just a galaxy rotation curve story. It is embedded in the early universe. It is present in the fingerprint of the cosmos when it was only hundreds of thousands of years old. On the largest scales, galaxies are not randomly distributed. They form a web, clusters, filaments, walls, and voids. This web emerges naturally in simulations where cold dark matter collapses under gravity, creating a network of halos and filaments into which baryonic gas falls. The gas then cools and forms stars, lighting up the dark matter structure. When we compare observed large-scale structure, galaxy clustering, weak lensing correlations, baryon acoustic oscillations with models, we find strong support for a universe with dark matter and dark energy in the standard cosmological framework. The details matter, though. The distribution of small halos, the number of satellite galaxies, the density profiles of halo centers, and the structure within halos depend on both dark matter physics and baryonic astrophysics. That is where the frontier lives. Cosmological simulations are not just pretty pictures. They are experiments we run inside mathematics and computing. We can set initial conditions consistent with the early universe, add physics for gravity, hydrodynamics, star formation feedback, and then let the simulated universe evolve. In dark matter-only simulations, we see the formation of halos with characteristic profiles and substructure populations. When we add baryons, the results change. Feedback can transform inner profiles, change star formation histories, and alter subhalo survival. Simulations are crucial for two reasons. First, they connect early universe measurements to late-time structures. They tell us how the CMB's initial perturbations become today's galaxy distribution. Second, they allow us to compare different dark matter models. Warm dark matter changes the formation of small halos. Self-interacting dark matter changes cores and halo shapes. Models with strong dark radiation can change growth histories. But simulations are also limited. Subgrid models for star formation and feedback are approximate. Resolution limits can matter. And when we interpret a small-scale discrepancy, we must ask, is this telling us new particle physics? Or is it telling us we do not fully understand baryonic processes? That question is not embarrassing. It is the honest frontier of the field. So, if you want to hold one calm thought about dark matter maps and simulations, it is this. Dark matter is inferred from multiple independent methods. Those methods have different systematics, and the consistency between them is part of why scientists take dark matter seriously. Dark matter news can feel intense. A headline claims a signal. Another headline claims it was a mistake. A third headline claims the mystery is solved, and the next day, nothing is solved. So here is a calm guide to what matters and what to look for in the coming years. If you see a claim that an experiment detected dark matter, the first question is not, is it exciting? The first question is, will another experiment using a different setup see it too? In direct detection, a real signal should appear in multiple detectors with compatible interaction models. The detailed rates may differ because target materials differ, but the underlying physics should align. In axion searches, a real line-like signal should be reproduced by another haloscope scan, ideally at a different facility, and should show the expected dependence on tuning and magnetic field conditions. In indirect detection, a real dark matter signal should appear consistently in multiple dark matter-dominated targets and should match the expected spatial distribution rather than known astrophysical source populations. Reproducibility is not a buzzword. It is the heartbeat of discovery. Dark matter claims fall into a few categories. It helps to place a headline into its correct category. Direct detection claim, an excess of nuclear or electron recoil events, annual modulation, or other detector signature. Indirect detection claim, a gamma ray line, an excess in dwarfs, a galactic center feature, a cosmic ray anomaly, a neutrino signal from the Sun, or similar. Collider claim, missing energy events suggesting invisible particles, often within a mediator model. Structure claim, a small-scale structure pattern suggesting warm, dark matter, self-interactions, or new physics. Each category has different typical pitfalls. Direct detection pitfalls include background mismodeling and detector systematics. Indirect detection pitfalls include astrophysical source confusion and propagation uncertainties. Collider pitfalls include model dependence and missing energy backgrounds. Structure pitfalls include baryonic feedback and measurement uncertainties. If you know the category, you know where to be cautious. The most powerful future is convergence. A direct detection hint plus an indirect detection hint that point to the same mass scale. A collider mediator plus a direct detection signal that align under one model. A lensing substructure pattern that suggests a cutoff scale consistent with warm, dark matter limits. An axion line plus complementary constraints from helioscope or laboratory searches that fit together. Convergence is rare, but when it happens, it changes the conversation. Many dark matter results are, we did not see it, so we rule out a region of parameter space. This can sound negative, but it is not. It is a narrowing of ignorance. If a detector rules out spin-independent WIMP interactions down to extremely small cross-sections at certain masses, it tells theory what is not true. If a telescope analysis rules out annihilation cross-sections for certain channels, it tells us which indirect signals are unlikely. If microlensing rules out a PBH fraction in a mass range, it tells us PBHS cannot dominate there. Each limit is a map boundary, and maps are progress. It is possible that a discovery could appear suddenly, but it is also possible that the next decade looks like this. We improve weak lensing precision and map matter more accurately. We measure small-scale structure better and learn whether certain tensions persist. We push direct detection to the neutrino background region and expand into new channels. We expand axion searches across wider mass ranges. We refine collider-mediator searches and better connect them to cosmology. This is still exciting because the dark matter problem is one of the deepest in science. Progress does not have to be a single dramatic moment. It can be a steady sharpening of the universe's outline. If you have listened this far, then you have walked through one of the most beautiful scientific stories we have. A story where light is not enough. A story where gravity is the narrator. A story where the universe shows us its mass by bending, by clustering, by shaping the growth of everything we can see. Dark matter remains a mystery, but it is not an empty mystery. It is a structured mystery, surrounded by evidence, constrained by data, and pursued by experiments that are becoming more sensitive every year. And whatever dark matter turns out to be, particle, field, compact object fraction, or something we have not yet named, its discovery will be a discovery about the early universe, the laws of physics, and the deep architecture beneath the stars. If you want more calm, deeply researched space stories told in this relaxed style, please like the video, subscribe to Early Science, and turn on notifications so you don't miss the next one.